So my experience in this area is that students have difficulty with conversions, and these conversions specifically. So we're going to try a couple of these just to see what you guys can do. We'll start with this one. I would like rotations per second converted to radians per second. And it should be no difficulty. In a few seconds I should come by and see what you have. It's a simple skill to be able to do. If you don't know how to do conversions, then I'm going to teach you a way. And for those of you who feel like you are complacent, the answer was 2 pi over 3, but you should have gotten a decimal answer to that, which is about 2 radians per second. Now, I know I have a variety of answers out there, but listen closely. That was just to see if you understood the conversion fact, and that's where I want to begin. I use unit multipliers for converting for a number of reasons, but one of them is because it's really hard to make a mistake with unit conversions. So if you don't know how to use unit multipliers, I'm going to explain it, and I'm going to explain it one time, and then I'm going to expect you to be perfect at it. All right, we'll see, because I'm going to test you on it. So here we go. If you're converting 1 rotation per second to radians per second, you don't have to convert the seconds. That unit's already good. You're only having to convert the rotations. So you need a conversion fact that goes from rotations to radians. I walked around and saw a whole lot of people with the number 180 on your paper. I know what you're thinking. You're wrong. This does not need to be passed through degrees. And I know that your conversion fact that you had ground into you in one of your math classes was pi over 180 or 180 over pi. We're not going to convert this to degrees in any fashion. In fact, we will never have an answer for an angular speed in degrees per second, ever. I want you to understand, degrees will only be used for angle measures. The only thing that's okay for angular velocity is RPM, RPS, and radians per second. Those are the only options. Radian is not a unit. How many of you understand that? Let me be very clear. I assume 100% of you know that, but how many of you understand that radians isn't a unit? Okay, so you were told it wasn't a unit. Were you shown why it wasn't a unit? So you guys never found a value for pi whenever you've been in school? Would have been elementary school, probably. You bring in the whole thing where the teacher said, find something in your house that's a circle, bring it to school. Did you do this?
Yeah, I think so.
I'm so sad. So only one of you did. It would be acceptable to say that the angular velocity is every 3 seconds. The problem is that as a unit goes, 1 over seconds has a name already called the hertz. Hertz is an inverse second, but it stands for an oscillation per second or a rotation per second, which is why for us, we write in something to indicate when we know our value is in radians, even though it's a unitless quantity. It's to indicate that it's not referring to a rotation and is referring to a specific angle measure in radians. We're going to be using angular velocity a lot in the next couple of days. What you must understand is anytime you're using it functionally within a problem, you must be in radians. Could you maybe write that down and show that you're listening a little bit? Because you'll screw this up, and I don't want you to. Anytime you see this appear in any formula that I write down, you must operate with radians as your unit. I may give you stuff in rotations per minute. I might ask for answers in rotations per minute. But while you're working the problem, you need to be in radians per second. So the first place I want to kind of apply that is right here at the horse. What you just found was the horse's angular speed. It was it 2 point what? What's that? 0.9? The angular speed of the horse, 2.09 radians per second. Now, apply that to both horses. Both horses had the same angular speed, but horse A was traveling at a slower linear speed than horse B. It's easy to figure out how to deal with that. One way is to just deal with the circumference. You guys all realize that no matter which horse you had, you could calculate their linear speed by taking the size of the circle they traveled in and dividing by how long it took to make that circle. That would give you the linear speed of both horses. But if you look at what I gave you just a moment ago, the whole idea of arc length equals angular displacement times radius. If you divide both sides of this by time, you could regroup this a little bit. This side would be in radians per second. I'm sorry, this side would be in meters per second. This would be linear speed. If we group this as delta theta over t times r, this would be angular speed. So you can get the tangential velocity of any object traveling on a circle directly from its angular speed. You need this. You need this. All right, we're going to use it a lot. All right. Now, I think it's very clear, but maybe not clear to you, so let me spell it out. This tells you, without having to do any calculation, that horse B is traveling faster than horse A if I'm interested in its linear speed, right? It's proportional to the radius. Since both horses have the same angular speed, the one further out is going to be traveling with a faster linear speed. I'm trying to be careful about my word choice here. I'm trying not to say which one's traveling faster. I'm trying to compare linear speed directly. So horse B has a higher linear speed than horse A, but they both have the same angular speed. The entire ride has the same angular speed, but the linear speed of horse A is different than the linear speed of horse B. Based on what we already know about centripetal acceleration, it might be clear that you have to hold on tighter to horse B than horse A. I'm not sure if it's clear or not, because R is how far away from the edge you are. That number's getting bigger, which would suggest that the acceleration would be lower. But V is getting bigger as you travel towards the outside edge. So it might not be obvious which horse requires you to hold on more. But you guys are smart kids. You could do a substitution here and get the centripetal acceleration in terms of the angular speed and not the linear speed. This is important. If you do the math here, you find out that you have an expression for the centripetal acceleration in terms of the angular speed of the object. And it should be very clear now that if you're on an object that's spinning, you have to hold on tighter if you're further away. That's what that says. All right, the three circled things are things you need to know. And they're not all on the equation sheet. Let me demonstrate where I need you to be able to do this. So here's an example. And this is straight off of an old AP exam. On an old AP exam, they had a problem with a record and a bug. There's a bug on the record. And the record was spun at a standard record spinning speed, which is 33 1/3 RPM. Now, for those of you who listen to records, why, I don't know, but that is the standard long play speed of records. Records came in, well, record players had 4 different speeds on most of them. They're all not arbitrary, but they seem arbitrary. They were 78 RPM. Those are the oldest records. Then 45s were singles, usually had one song on each side. And there was long play records, 33 1/3. And then there was ultra long play, but I've never seen a record that was 16. But these were the standard spin rates of record players back in the day. Not to be confused with the standard spin rates of CDs, which are usually up around 400 RPM, or DVDs, which spin even faster. Blu-rays spin about the same speed as DVDs, but they have the information more tightly packed. So I don't know if you guys even know what these things are. But I mean, if you're listening to music on a CD, that's probably pretty old school for most of you. If you're listening on a radio or on a record, you're just trying to be ironic, or I don't know. There's probably a better word to describe it. Records are neat. Mr. Lou likes them. He has a record player in his office. I look at it and laugh and think it's probably neat. But there is something missing. You guys will never have the experience, unless you have a record player, of buying a record, which were big. And it's hard to explain this because if you listen to all of your music stolen, or you listen to it on an app, or you listen to it online, you miss the idea of being the first one to bring the record home, tearing off the shrink wrap. All original records in the 70s opened up, so there was a massive inside for you to read. Oftentimes, the bands sweated what they put on the inside of this and hired expensive artists to do all the artwork. It was amazing to take that big thing out, and sometimes there was liner notes on the inside. You put it on there, you had no idea what you're going to hear. It was a different time. Now, it's not the same. I'm a little disappointed. I like music. Obviously, I listen to music all the time, and I think that both Spotify and Apple Music have gotten the whole experience wrong. You don't get to enjoy music the same way. I think they could have a richer experience. It would be more fun, but it doesn't seem to be there. All right, that's enough of a brain break. Back to work. Here's what I want from you. If the spider is 12 centimeters away from the center, and his little spider body has a mass of 15 grams, with how much force does he have to hold on to the record? Okay. If I were you, I'd write the question down so that you have reference for it later. Again, I have a spider that's on a record. The record is spinning at 33 1/3 RPM. That would be sentence 1 of my problem. The spider is located 12 centimeters away from the center of the record, and his little spider body has a mass of 15 grams. With what force would the spider have to hold on to the record to not be thrown off? You have everything you need to do this problem. Whether you know how to do it or not, everything you need is there to do this problem. Now, I would encourage you to start this problem the way we've started all force problems, with the free body diagram. And begin the problem that way, because these problems are going to get more complicated. I'm starting with the simplest one I can think of. So I'm looking at the spider from the side, and he's experiencing, I think, obvious forces: normal force and weight. But he's having to hold on to the record to keep from being flung off, so he's also probably experiencing a force in this direction. Now, I don't know what force this is. I didn't say. I'm saying that the spider's holding on. Perhaps he's grabbing a little groove of the record. By the way, how many grooves are on a record? You understand that a needle sits in a groove. The groove is chiseled with the actual sound form that's going to be played, and a needle is attached to a magnet and moves inside a coil of wires to generate a small current inside the coil of wires. That's where the music comes from on a record. How many grooves are there on a record? There's 2. 1 on each side. It's a spiral. It has to be to draw the needle through the record from the outside to the inside. So it's one long spiral on each side. What's interesting is CDs are the same. It's a spiral of dots, but CDs start from the inside and play to the outside. I don't know why. Same with DVDs. I do know why, but it doesn't matter for our discussion here. Start here, right? Is this a first law problem or a second law problem? Second law problem. You now have to ask yourself an additional question, and that is the object traveling in a circle or not? It's an important question to ask, and I'm not sure that you'll need to always ask it, because you'll probably become adept at it. But if you know the object's traveling in a circle, you should throw that little C here, reminding yourself this is a centripetal acceleration problem. So now when you ask yourself first law or second law, be mindful that there's two different ways to deal with the second law. One for an object changing speed and one for an object traveling in a circle. Be prepared. I'm going to trick you on the next test. I'm going to have both, and you'll have to be able to tell the difference. If you know the object's traveling in a circle, then you know that we're talking about a centripetal acceleration, of which you will have two choices. You can replace the acceleration with v squared over r, or you can replace the acceleration with omega squared over r. It doesn't matter which one you choose, but you should choose the one that matches what's been given in the problem. This problem gave an angular velocity, which suggests this would be a better, oops, I wrote it wrong, and nobody corrected me. And I wasn't actually trying to trick you, I was just in a hurry. Change your notes. Change your notes. If you just fell asleep and aren't paying attention, change your notes. All right. It doesn't matter which one of these you choose, but I would choose the one that's given in the problem, because you can always convert from one to the other, but why make an extra step for yourself? You will likely forget to do this. So if you have a formulation that uses linear velocity and they give you linear velocity, use that one. And since you have a formulation that uses angular velocity, if they give you angular velocity, then use that one. This problem gives you angular velocity. So now my net force equals m omega squared r. And I can look at the forces that are acting on my system. I've got whatever the spider is doing to hold on. I've got the normal force on the spider. And I've got the weight of the spider. Seems to me like this is the one that's in the x direction and it's 0 in the y direction. Right? The spider is still sitting on the record, so the net force in the y direction appears to be 0. And this is the force in the x direction. There's only one force in the x direction. That is the force that the spiders use to hold on. And it seems to me that if you followed that set of steps and got to here, you'd be able to find this force. And this is what the question was asking you to do. Find the force that the spider uses to hold on to the record. Now, I'm going to leave that to you right now, because you're going to screw this up if you haven't been paying attention. I've given you everything you need to do this problem correctly. Try it. We should all get the same number. But I'm confident that only half of you have been paying real attention. I can just tell by the way you're looking at the board. It's a little bit painful. We have the mass, we have an angular speed, and we have the radius. Seems like this was plug and chug, yet no one got it right. That hurts me in my heart a little bit. Let's start with the fact that none of those in the proper unit. Not one. The mass has to be in kilograms, not grams. The distance, the radius, has to be in meters, not centimeters. And 33 1/3 RPM has to be in radians per second, not rotations per minute. Everything had to be converted. Some of those are easy to convert. For example, the mass, that's 0.015. I divide 15 grams by 1,000 to get kilograms. So all of you who didn't pay attention during the whole conversion thing, hurting my heart. Centimeters to meters, you divide by 100, so that's 0.12. Now this bad boy in the middle, I don't know if you did this right or not, but it's about 3.5 radians per second. I don't know what you got, but based on some of the numbers I saw, it wasn't 3.5. Because if you just didn't convert these two, you should have gotten some version of 219 as your answer, with the decimal place somewhere around there. So that suggests you didn't convert the rotations per minute correctly either. So look, this is not the problem you have to do in here. The problem you're going to have to do is to figure out the coefficient of friction between the spider and the record. We're just on step 1 of 3-4 more steps. You got to get those conversions nailed. So if there's something you don't know how to do here, you should ask, so you don't look silly the next time. But I'm going to do the 33 and a third conversion. All right, go ahead.
Capital R is radius.
Radius of curvature, yes.
Oh, does it have to be capital?
No. I switch between capital and lowercase all the time on purpose. It's not to confuse you, it's because they do it on the test all the time. Sometimes lowercase, sometimes capital. You need to know what it represents. The symbol is less important. Okay? So let's do the first thing. Let's convert that 33 and a third. That's rotations per minute. Again, I use unit multipliers. So the first thing I'm going to do is I'm going to recognize that I need two multipliers. One to convert the rotations and one to convert the minutes. I want to be left with radians per second. So if you've not done this or you're not good at this, look, set it up like this. Know what your destination's going to be. I have rotations here, I need radians. My first multiplier is going to make that conversion. I need to cancel out the rotations, so I put it on the opposite side of where it is in the original unit, bless you. And I'm going to put what I'm shooting for at the top. Sometimes you might have to walk your unit conversion through more than one step. Next week when we do gravity and have to go from like days to seconds, you might have to walk that through a couple of steps if you don't know how many seconds there are in a day. It depends on what multiplier you know. I know the direct multiplier from radians to rotations, which is why whenever I saw 180 on anybody's paper, I know you're screwing it up and you're not listening to me. One rotation is 2 pi radians. That's the only conversion you need. Don't dance it through degrees. Doesn't have to even go through degrees at all. So stop thinking what you learned in your math class is going to help you here. It's probably just getting in the way. Minutes on top to cancel the minutes on the bottom. And I want to be left in seconds. For every 1 minute, there are 60 seconds. You know these conversion facts, so don't ever want to think it's because you don't know how to convert from one to the other. You don't know a procedure. You keep asking yourself, should I divide or should I multiply? It's the wrong question. When I had 15 grams and I wanted kilograms, some of you multiplied or divided and didn't know what you were supposed to be doing, but look, a unit multiplier will make sure you don't get the answer wrong or look silly. I want to get rid of grams. I want to be left with kilograms. You know which one's bigger and which one's smaller. You know it's got to be the 1 on top and 1,000 on the bottom. Now you won't look silly. Because to me, you look silly when you can't do a simple conversion like this. Or maybe you didn't think to do 12 centimeters to meters. But you have to. You have to think about all of these things. Cancel centimeters, left in meters. There are 100 centimeters for every meter. Now this came out to be 3.5. So I don't want to spend time on this part. This is the part you're supposed to have come into class knowing how to do. So you can't make this mistake again. But I hate to do this to you. I see many of you writing. You should check, make sure the answer works out. But when you put your 3.5 here, make sure you square it. Because at least one of you made that mistake. You'll get the right answer. And I got point something, I think 0.02, yeah, 0.022 or 0.0219. And that would be newtons. That's how much force the spider has to apply to stay in place. I'm going to test you right now because I think you're going to mess this up. Okay? If I had, let's go with 300 radians per second, can you make that rotations per minute? I'm asking this on purpose. In fact, let's not do it this way. Let me make it even simpler. 3 radians per second converted to rotations per minute. Do the conversion, circle it on your paper. Unit multipliers, get them out there. There should be 2 of them. One to deal with the rotations and one to deal with the minutes. Now, circle your answer. You should be almost done. It shouldn't take that long. If you haven't done it by now, then I don't know what's stalling you. We just did the exact problem in reverse a second ago. Now, clear out your calculator, please, and do something for me real fast. I want you to do it real fast and turn your calculator over. Okay? Here we go. Do this, then turn your calculator over. You done? Should only take a second. 3 divided by 2 pi. Turn your calculator over. Everybody calculator over? Looks like it. Look, I don't know what your number is, but it should be a half. This is 3 divided by 6. Right? Turn your calculator over. If you don't have a half, slightly less than a half. If you don't have that, if you have a bigger number in there, you don't know how to use your calculator. Okay? Because there's a group of you in the room who have something like that's around 4.5. Because you did 3 divided by 2 times pi. Because you don't know how your calculator works. If you want your calculator to work, you might want to start putting a parenthesis around that or just using 6.28. Or you will look silly. And we don't want to do that. You don't want to sit there going, I don't know why I didn't get 28.7 rotations per minute is my answer. I'd hate to find out that that was the reason why you didn't get 28.7. 2 multipliers. 1 rotation for every 2 pi radians. 60 seconds for every 1 minute. You had to divide by 2 pi, multiply by 60. Look, I didn't even walk around to see who made this mistake. I just don't want the mistake made again. Does everybody understand? And I'm willing to pop quiz you every day to make sure. I won't. But if I see these mistakes on the test, you know I'll go crazy. I'll be berserk. I'll be so angry. This is going to be over the multiple choice section of the test, and you understand that you guys work fast there. This is how they're going to do it to see if you can do the stuff right. This is where it'll appear. So, question. This is what my actual expectation is for this question. There is a coefficient of static friction of 0.6 between the spider and the record. If the record is being spun at 45 RPM, what's the furthest distance away from the center the spider can safely walk? I'm going to say that all over again because this is the kind of problem you're going to have to solve. So again, the spider is going to walk on the record, and he's going to try and choose where he's going to walk because he's a spider and he's concerned about such things. There's a coefficient of static friction of 0.6 between the spider and the record. What's the furthest away the spider can walk without being flung off the record? Everybody understand the problem? Or at least know what the problem is asking? Now, this is a tough one. There's a lot that has to be done here. Now, almost everything we've done up to this point has been leading to this kind of problem. The biggest mistake you're going to make is not recognizing that this is a Newton's second law problem. Even though the spider is using static friction to stay on the record is moving. So the spider is accelerating. This is a tough question. I didn't post your homework last night because, to be honest with you, I got busy. Your homework culminates with questions like this, but it starts with easy ones. So, how do you prove pi? It's really not hard, and you should have done this as a kid. It's really super stupid simple. You take a piece of string and you tie it around something that's a circle, right? And then you take that thing over here and you cut the string and you see how long it is, because that gives you circumference. And then you take a ruler and you take the ruler and you try and measure the diameter of that circle thing you brought to school. And that has to equal pi. Now, this proves what pi is, and you can do so in the third grade. And the best part about it is that if you do it in the third grade, everybody brought something different that's a circle in the school, and everybody got the same answer for pi. And they're all gee-whizzing it. Now, this is not particularly accurate, but you'll get 3, and it's really all you need to show. You may not understand this, and I don't care. I want you to be smart people. And pi shows up everywhere in the universe. It's hard to understand the nature of it as a fundamental constant. And you might not appreciate how important constants or fundamental constants are in the structure of the universe, but there are constants that are not real constants, like g. G is not a real constant. Us saying that 9.8 meters per second squared is important is not. The only reason it even exists as a number is because we live near the surface of the earth. It is not universal. It's not something that exists everywhere in the universe. And more importantly, it only exists to humans because it has to be in meters and seconds. If you lived in this country 10 years ago, we would have taught you 32 feet per second squared. Because for a while, we were still using English Standard when I was a teacher. So it wouldn't have been unusual for the 32 to be the important number and not 9.8. You're going to need that.
Mr. Bishop really made me wait 2 minutes to get back.
Now, there are a variety of other constants that are universal, meaning that they are part of the fabric of the universe, are the same everywhere in the universe, like one you haven't seen, but something like the mass of a proton. We think that's the same everywhere in the universe. So that 1.6 times 10 to the 27 kilograms, we think that's pretty important. Same with the mass of the electron. 9.11 times 10 to the negative 31 kilograms. Negative 27th. We think these are the same everywhere in the universe. But again, that's only relevant on Earth, right? Because it's in kilograms. How do you tell somebody on another planet what a kilogram is? So there are constants that are only important to us because they're measured the way we measure things on the Earth. Pi isn't like that. Pi will be the same value everywhere in the universe and has no units. So it doesn't depend in any way on whatever the chosen unit is for whatever world happens to be, having circles on it. There are only a couple of things that are like that. The exponential, e, 2.7, it's a unitless quantity. And where it comes from is an interesting story. It's a non-terminating, non-repeating decimal, just like pi is. You can generate it a number of ways in a machine. But why does it exist? Why does things that decay, radioactive decay, which is a great way to measure E, why is it that number? Nobody really knows. Nobody has an idea. There are 2 or 3 other numbers that are like this, that are interesting. The number 1, you might not believe it, is very interesting. And the empty set, very interesting. These are things that have fundamental meaning in the universe. Existence, non-existence. And we use it for all computers, the idea of a bit. The ability to create and encode something based on a bit. And maybe, if you really want to think about it, it might hurt your head a little bit. Pi is a non-terminating, non-repeating decimal, which means if you carry it out far enough, there is the entire works of Shakespeare encoded inside of it. By definition, they have to be there because every possible combination of every possible number in the universe has to appear in pi. That kind of stuff makes my head hurt. But every single college I've ever gone to, some yay-hole professor has pi calculated to like 1 billion digits taped around their inside of their office, because they have become that fascinated with the idea of this non-terminating, non-repeating decimal as a fabric foundation of the universe. You may not believe this, and I don't care. Pi is somewhere inside the speed of light. It explains why electromagnetic radiation propagates at the speed at which it does. It also establishes why radio frequencies work the way they do for your phones. Pi is embedded in all of that somehow. And it's weird. Why would it show up there? It does. It shows up in a lot of interesting and unique places that you wouldn't expect. E shows up in all sorts of places. It shows up in things like air resistance and drag. It's part of the whole nature of how drag forces work. Why? I don't know, but it does. It shows up in a lot of interesting places. It also shows up in electronics as to how circuits, when you flip the switch, how long till the light actually turns on. You think it's instantaneous. It's not. And there's a rise curve that determines how long it takes for circuits to actually function. E is embedded in that somewhere. How? Why? It just is. It's embedded in the fabric. And neither of those have units or anything. So when we talk about, why do radians not have units, there's a fundamental reason why radians don't have units. It's a conversion. And if you haven't seen why it's a conversion, look carefully. You know this formula. Familiar to you? The circumference formula. What you understand is that that's not what that formula is. It's arc length equals angle displacement times radius. That's what that formula is. I doubt you learned it this way, but this is where the instruction begins for today. So I would write these things down because I'll expect you to know this. Good. I think the message coming through. The other part was just me talking about how fascinating numbers are, but this is going to be important. If you want the circumference of a circle, you would have to have a full displacement around the circle, which is equivalent to 2 pi radians. The fact that radian is a unitless quantity is not just implied, it's required. In this case, the arc length acquires the unit that radius is measured in. So the value of the angular displacement can't be in any units. That's why radians is used here. It's not a unit. 2 pi is a physical representation of an entire circle, and therefore has no unit. It applies to all circles regardless of their size. So the angular displacement isn't a unitless quantity. We call it radians so that we know that there's a placeholder there that represents angular measure. So when we are working with radians, you write out the idea of radian, even though it's unitless. It would be okay to say that going around a circle is 2 pi per second if you go around once per second. Or even in our last